Hi, hello everyone. So we will continue our lecture today on reinforced concrete beam. So in this subchapter, we are going to analyze the stress and strain in reinforced concrete beam under pure bending. Alright, so most of the concrete beam that's subjected to bending moment are reinforced by steel rod. So you can see here, this is the illustration of reinforced concrete beam, where this is the concrete. Okay, so that is the steel rod. Okay, so steel rod is used to reinforce. Okay, or I will explain later how the steel rod is used to support the tensile stress. Okay, the tensile stress when the beam is subjected to pure bending. Okay. Alright, so for your information, the concrete is strong in compression. So concrete basically in general is strong in compression, but the concrete is weak in tension. So this is why we apply the steel rod, okay, so that the tension force or tension stress will be supported by the steel rod. Alright, so the steel rod carry entire, so by adding the steel rod, this steel rod will carry the entire tensile load below the neutral surface. Okay, so let's say this is the neutral axis. Okay, this is the neutral axis. Okay, and then assuming that the concrete is subjected to positive bending moment. Okay, positive. What is the positive bending moments? Means that if you have a beam, okay, and then the moment will be in this direction. Okay, so that is the positive bending moment. Okay, so what happened after deformation? It will look like this. Okay, this is after deformation, and the upper part will be in compression and the bottom part will be in tension. Okay, so assuming that this beam is subjected to positive bending moment, so the upper part here will be in compression. Okay, compression, and below the neutral axis, okay, below the neutral axis will be in tension. So since the concrete is weak in tension, so we assume that all the tensile load or tensile stress will be carried by steel rod. Okay, so we can transform from the first figure here. Okay, we can transform into this one. Okay, in this one, where we remove all the parts of concrete beam which is in tension. Okay, so all the concrete here that is in tension, okay, we remove from the analysis, because we assume the concrete cannot support any load, any tensile load. Okay, so only the steel rod will carry the tensile load. So this is basically is the rod steel that we already transform. Okay, that's already transformed into concrete. Okay, because if we cannot if we are not transform the steel rod into concrete, so that we cannot straight away apply the fractural formula sigma equal to my over I. So this is why we transform the steel rod into the equivalent concrete. Okay, So the detail how to transform from the steel rod, okay, from the steel into the concrete, basically is we already discussed in the previous video. Okay, so I hope you still remember on that. So in the transform section, the cross-sectional area of the steel AS is replaced by the equivalent area NAS, where N is ES over EC. Okay, so let's say the area for the steel rod, okay, the area for the steel rod here, okay, is given by AS. So after deformation, so we have to multiply the area for the steel rod that is transformed into the concrete will be equal to NAS. Okay, where N is equal to, so N is equal to the Young modulus for the steel over the Young modulus for concrete. Okay, represented by ES over EC. Alright, so next slide. Okay, now in order to determine the stress in the concrete beam, reinforced concrete beam, okay, where the stress is given by y over I, or sigma max is equal to mc over I. Okay, so in order to apply this equation or flexural, this is what we call as a flexural formula. So in order to apply the flexural formula, so first we have to determine the location of neutral axis. Okay, we have to determine the location of neutral axis so that we can determine the value of I. Okay, so without knowing the neutral axis, the location of neutral axis, we cannot determine the moment of inertia. Alright, so now let's consider this figure. Okay, so this is basically the figure from the previous slide. So we have the concrete, the upper part of the concrete, and also the steel rod that has been transformed into concrete. Okay, alright, so we denote this length as a x, okay, where the x is measured from the top surface of the concrete to the neutral axis. Okay, neutral axis, and this is the B, the base. Okay, and the total length here from the top surface to the steel rod, or the steel that has been transformed into concrete, is equal to D. Okay, so for this case, from here we can say that the distance from neutral axis to the steel rod, okay, that has been transformed is equal to D minus X. So this is the length D minus X, because this is the D and this is the X. So this length is equal to D over D minus X. Okay, we have the equation for moment of inertia. Sorry, we have the equation for centroid, where the centroid is given by y bar is equal to the summation of y A over summation of A. Okay, I hope you still remember here. Okay, so let's consider here first. Okay, I want to explain how we get this equation basically. Okay, so this equation basically is from the centroid equation, but I will explain how you get this equation. Okay, so we have the equation the centroid equal to y bar equal to summation of ya over sigma A. Okay, so let's say let's consider the T beam first. Let's consider the T beam first. Okay, so what is the y bar? So y bar is measured from the reference line, or the datum, okay, to the neutral axis or to the centroid. Let's say here is the centroid. So that will be the y bar. Oh, y bar, yes, that's the y bar. Now, and okay, since this is the centroid and the neutral axis must pass through the centroid, so the location of neutral axis will be like this. This is for the case of TB. Now, what happen if, okay, if I choose the reference line, okay, is what happen if I choose the reference line is at neutral axis, okay. Okay, so what it means is what happen if, okay, let's say you have a T shape of beam, okay, and then I choose, yes, I don't know where is the location of centroid, but let's say here is the location of centroid and that is the neutral axis, and then I choose the y bar, the reference line is located at neutral axis, okay. So if I assume the reference line is located at neutral axis, so the y bar will be equal to 0. Okay, y bar equal to 0. So this is the case when we assume the neutral axis, the reference line is located at the neutral axis. Okay, so we don't know the location of neutral axis, but we assume the reference line. So for this case, we take the reference line or the datum is at the same location of the neutral axis. So what happened? This equation, okay, the central equation, which is here, this one, y will be equal to 0. Okay, will be equal to 0. Why? Because the reference line is located at the same location of neutral axis. Okay, so y bar is equal to 0 is equal to the summation of y a over summation of a, so that from here the summation of y a is equal to 0. Okay, alright, so we can apply the summation of y a equal to 0, okay, to determine the location of neutral axis. So this is basically come from the summation of y a is equal to 0. Okay, so we can see here, okay, so for example, so we have a two part here. This is the simpler part number 1, this is simple part number 2. Okay, so if we determine the ya for the first part, so ya is equal to b times x, so b times x, and then y is measured from the centroid of the shape 1 to the neutral axis, or to the centroid of the overall beam. So that will be the y for part 1. Okay, here, this one. So that is the y part 1. Okay, and then for part 2, so the area is, okay, the area A is equal to NES. So NES, and then the distance, okay, from the centroid of part 2 to the centroid of the overall beam, okay, that is the y for part 2 is equal to d minus x. So that is the y2, and then equal to 0. So why negative? Why we have negative here? Because one is in this direction, okay, the other y is the opposite direction, so we have minus. So if we expand the equation, let's say this is the equation 1. So if we expand this equation, we get this one. Okay, we get equation number, let's say this is equation 2. So we get equation 2. So if we know the value of B, the value of N, we can calculate the value of N, we can calculate the value of AS, and then D normally is given, and AS can be calculated, so we can calculate the value of S. Okay, from this equation, okay, we can determine X. Okay, so once we know the X, so we know the location of neutral axis. Okay, we know the location of neutral axis. So this is how we determine the neutral axis, by determining the value of X. Okay, so finally we can apply the Flexural formula, sigma equal to my over I, to determine the stress in the beam, okay, in the concrete and also in the steel. So for stress in concrete, so that's equal to the sigma x, which is equal to my over I. So we can straight away apply the Flexural formula to determine the stress in concrete. Okay, so for the stress in steel, so that's the steel, so we can apply the same equation, which is the my over I, but we have to multiply by the N because we transform. So remember, in the previous slide, we transform the steel rod into into concrete. Okay, in concrete, so that is why we have to multiply by N, transformation factors. Alright, so location of reinforcement steel. So as I said, concrete, okay, concrete is strong in compression, okay, but concrete is weak in tension. So the location of reinforcement or steel rod, okay, normally we will locate, okay, sorry, normally for the concrete beam, we will locate the steel rod, okay, at the tension part of the beam. Okay, so for example, this is the concrete beam, and then subjected to the distributed load. Okay, distributed load. This is a distributed load. So what happened? The beam will be deformed like this. Okay, deformed like this, and the upper part will be in compression. The bottom part will be in tension. So in order to support the tension load or tension stress, so we put the steel rod, okay, this steel rod only at the location of where the stress is in tension. Okay, so same thing here. If you have the cantilever beam, concrete beam, so subjected to distributed load, so the upper part, for this case, the upper part will be in tension and the bottom part will be in compression. So we put the steel rod at the upper part, okay, upper part of the beam, because the upper part will be is in tension. Okay, so same thing to here. If you have distributed load, and then the beam is support at 3 points, so this is how the deformations of the beam looks like. Okay, so for this part, okay, let's say this is point A, point B, and point C. For point A and B, the top or the upper part will be in compression. Okay, in compression. The bottom part will be in tension. So that's why we put the steel rod at the bottom part. And then somewhere at point B, here will be in tension. And the below the neutral axis will be in compression, so we put steel rod at the tension part, and similar to portion BC, the upper part will be in compression, the bottom part will be in tension, so we put the steel rod below at the tension region. Okay, now we proceed with the stress concentration. What is the stress concentration? Stress concentration occur at location where cross-section suddenly changes. Okay, so previously we assume the cross-sectional area of the beam is uniform, but if we have the case of like this, for example, we have the notch, okay, notch, okay, and then hole, example hole, or fillet, okay, for example here. So all this discontinuity will develop the stress concentration. So what is the stress concentration? So it means that the stress will be concentrated at some point of the at some point in the beam, which is at the discontinuity or irregularities shape. Okay, shape. For example, here for this case, the stress will concentrate at this point, and for this case, the stress will concentrate at here and also at here. Okay, so that's what we call as a stress concentration. So for the case of this beam, okay, if we have the beam with sudden changes in cross section, for example here, okay, notch, if we have a notch, hole, and fillet, so we cannot straight away apply the Flexural formula sigma equal to my over I. So what we have to do is we have to multiply by the factor k, okay, the factor k here. Okay, so what is the k? K is called stress concentration factors. Okay, so again I repeat, if we have the sudden changes in cross section, for example we have the notch, hole, or fillet, okay, this is a example. So in order to calculate the stress maximum, stress maximum, so it is given by K multiplied by MC over I, where the K is the stress concentration factors. Okay, so how to determine the K? K can be determined from the graph. Okay, from the graph. For example, this is a case of fillet with radius R. So you can get the K from this graph. So this is the K, but the information that required to determine the K is R over D and also capital D over D, okay, which is the radius of the fillet over the small d here, and then you also need the information of capital D over the small d here, so that you can determine the K. Okay, so for example R, for this case, R over D is equal to 0.15, and then given the value of capital D and small d, D over D equal to for example 1.1. So you can draw here 0.15 for R over D, and then for capital D over D is equal to 1.1, which is this line. Okay, this line. So you go to this line, and then you can get the value of K. So that will be the value of K. Okay, maybe 1.42, something like that. Okay, and then if you have another shape, notch, for example, the beam with the notch, so you can apply this figure in order to determine the K. Okay. Alright, so this is the illustration of stress concentration. Okay, you can see here, let's say you assume this is the beam, and then subjected to load or bending moment. Okay, you can assume this is a beam subjected to bending moment and produce the stress. Okay, and then imagine that one line here represent by, for example, 1 megapascal. Okay, 1 megapascal. So you can see here at this point, okay, there are several lines, 1, 2, 3, maybe 3 lines. So here will be the, if one line represent 1 megapascal, so at this point, because 3 line is concentrated here, so the stress will be 3 megapascal. Okay, what happened to this line? What happened to this location? Because we have only one line, so the stress is equal to 1 megapascal. Okay, so you can see the line is concentrated at this point and also this point. This is what we call as a stress concentration point. Okay, so we can see the stress distribution using the finite element, for example. So you can see here the red colors means the highest stress value. Okay, so also for the fillet, okay, you can see the line, the distance between the line is very close, where we can say the stress, okay, the line of stress is concentrated at this point. So this is the illustration of stress concentration. All right, so I think that's all for this video. So we will proceed to the next video with some example of analysis of reinforced concrete beam. All right, thank you.